Okay, so following on from the last couple of clips, we're going to look at a more practical application of adding two forces together and finding out what the resultant force is. So this little model here represents what you might see out in your field. We have two poles, imagine they're in the middle of a field, and you've got a cable between them, and this cable sags in the middle and it has mass, and this mass is pulling down towards the centre of the earth, and it's pulling a force on this pole and it's pulling a force down on this pole here. One of the problems though with cables when they're suspended between poles is the wind, and the wind adds an extra force to it. So if I just blow some wind on there, you can see that it's now bending out, and depending on the angle of the wind depends on the force applied to the cable. Let's assume the wind is horizontal, then the cable will get to a certain angle. If I try and show that like that. So what we're going to do is try and calculate the value of that resultant force and the angle on the cable. And that helps engineers work out how to apply various stays to the poles at the right angle in the field. So let's have a look at that then. Okay, so remember we had the camera at the end, so let's imagine we're looking down towards right through the cable that's suspended, and it's going to have some mass, usually in kilograms. This cable is usually measured in kilograms per meter, and then we have the wind going that way, and we have the mass of the cable coming down. Now wind is often given in newtons, so let's say the wind is 762 newtons, and let's say the mass is 176 kilograms. Well, it's like what we did earlier. We need to create a little rectangle here, and the resultant force is going to be something like this. Now it's not to scale, I've just shown it as a sketch here to show what we're doing, but it's not to scale. So the resultant force is here, and the angle that we're interested in is here, because this is the horizontal. You're usually always asked for the angle relative to the horizontal. So to find out, before we go ahead with the calculation, we need to get both of these units the same. This needs to be converted into newtons. So F on the cable, call that equals mass times acceleration equals 176 times 9.81. There we go with that. 176 times 9.81 equals 1726.56, and the unit is now newtons. So just like last time, we've got a downward force of 1726.56 newtons, and of course this length is going to be the same because it's a rectangle, so that's 1726.56 newtons. So from Pythagoras we can now calculate the resultant force from a squared equals b squared plus c squared, or A equals the square root of B squared plus C squared. A equals $17.56 plus 762 squared, and that's the square root of all that. Do that on your calculator. But I've already got that left on the calculator from last time, so I just square that. Plus 762 squared, that's the total, and then I find the square root, which is 1887.23 newtons. So the resultant force is 1887.23 newtons. Okay. Now I'm interested in this angle. Got to find the angle with the horizontal. Well, we know that tan theta from before equals opposite over adjacent. So this is opposite, 1726.56, and adjacent is 762. Divide that. 1726.56 divided by 762 equals 2.265. So therefore theta equals the inverse of that, 66.18 degrees. Okay, so I'll put a few more examples of those on solar, so take a look at those. Thanks very much.